We're going to talk about solubility and complex ions. The lab that we're going to do on Thursday is a complex ion lab, where we try to determine what is it's an equilibrium constant between silver and ammonia as the reactants and the silver ammonia complex is the complex ion. So let's get rolling. Allergies? Yeah. Remember when we talked about the equilibrium constant? That's a generic constant. I mentioned one of them. I'm pretty sure I mentioned one of them as an SP. It's called a solubility product. If you start off with a solid, that's okay, but let's use one that we're going to be more familiar with. You start off with a solid and you put it in solution. There's an equilibrium set up between the solid that's sitting on the bottom and whatever part of it is dissolved in the solution. I mean, in first semester, we talked about it's either soluble or insoluble. And I hope I mentioned at that time that there's a gray area in between. And that's where we're going to work with today, the gray area where you have slight solubility. In other words, just a few ions of silver and chloride actually go into solution. Now, we would classify that as insoluble for the purposes of separating mixtures of metals. But as a matter of fact, most of it is still over here. You have just a tiny amount on this side. And if we write the solubility product for this reaction, we only get the product side. Because solids don't count. All right. That's why we call it solubility product, because it's always just a product. There's no denominator. Now, our example here is bismuth sulfide. Now, it's going to have some powers attached to it. The bismuth is going to be squared and the sulfide to be cubed because of the coefficients in the balanced equation. That's a solubility product. Now, and for a given temperature, this is constant. But when we talk about solubility product versus solubility, solubility product is this expression. Solubility is usually in molarity. How many moles of this can we dissolve in a liter of water? We're going to stick with water. Right? Solubility is like moles per liter or molarity. Right? What's the molar solubility of silver chloride? They're related, but they're not the same values. And just because the solubility product is large doesn't mean that the solubility is also large, because the solubility product may have powers associated with it, and that could inflate the value. So you could have comparing different salts going into solution. You could compare the KSPs and find that, well, one of them has a large KSP, but when you calculate the actual solubility, it's very low. Okay, and we're going to do that. Just a minute. Here we go. Solubility can also be expressed as mass per volume. In fact, if you look up the solubility of of different slightly soluble compounds in a reference manual like the CRC handbook, it will probably be expressed as grams per 100 milliliters of water. So how many grams of that salt will go into 100 milliliters of water at a given temperature? And the second reason, of course, is the powers. And when you have a balanced equation, you may have coefficients that go into this expression and inflate the value. I'm going to let that go for now. We're going to talk about that in detail in a minute. All right. So let's calculate the solubility of silver chloride. Well, I shouldn't have erased that. I'm going to need it. There's our balanced equation. And our KSP for silver chloride is given as 1.6 times 10 to the minus 10. And that's going to be equal to silver ions times chloride ions. Right? They're both coefficients 1 and 1, so the powers are 1 and 1. All right. How do we calculate the solubility? Here's our equation. Now, we made a big jump. We made a big jump from KSP expression to solution for the solubility. It's based upon the ice table. So if I bring ice down here, let me put it over here. You'll get to see a pattern. We'll do the ice table for a couple of times, and you'll start seeing a pattern to where you don't necessarily have to write the ice table every time you want to do it. But if we have initial amounts here, of course, they're going to be 0 before there's any solubility at all. And that one doesn't have a value. But if we want to express the solubility of that compound in molar terms, in molarity, then we'll say, all right, we're going to lose some of this as a concentration of molarity, right? That's going to be molarity. And since they're 1 to 1 to 1, we're going to gain this much molarity over here. Right? Okay. So this is going to be 1.6 times 10 to the minus 10 minus something. This is going to be S. That's going to be S. Okay. So now you see where this expression comes from. We used X there, but it's S. S is the same thing. This term doesn't even enter in, right? I mean, it's true, but it's not part of the expression because this is a solid. So we only have to include S times S, which is S squared. So if we take the square root of both sides, we'll find out the solubility here is the square root of 1.6, which in our slide is 1.3 times 10 to the minus 5. That's the solubility of silver chloride under the conditions where this KSP was developed, probably standard conditions, 25 degrees Celsius. All right. How about silver phosphate? All right. I think we have a pattern in mind now. But silver phosphate is a different formula. Right? PO4. This has a 3 minus charge. That's a 1 plus charge. So we need 3 silvers. That means we're going to have 3 here and only 1 there. Okay. That would be our balanced equation. Let's see. I think we show it next. No, we don't. That's a good thing I wrote it up there. Okay. Now, what would that expression be? Well, let's see. KSP is going to be different. 1.8 times 10 to the minus 18. 10 to the minus 18. And then these values are going to change also. We have silver ions in equilibrium to the 3rd power. And then phosphate ions to the 1st power. Okay. So maybe we better write the ICE table for this one. Because we really haven't established a pattern yet. All right, so if we start off with 0 here and we lose one of these, oops, what possessed me to do that? One of these, how many silvers are we going to get? Lose one of those, we get 3 silvers, right? We get 3 S's. Right? And we still get just 1 phosphate. So that doesn't count. We're only interested in 3S here and S there. So if we plug those in, 3S cubed times S is what? What's 3 cubed? 3 times 3 times 3. 27. 27. And then S cubed times S, the first power, is S to the 4th power. So now to find S, we divide both sides by 27. I might as well do that. Let's make some room. Let's take it step by step for this first one. All right, so this is going to be 1.8 times 10 to the minus 18 divided by 27 equals S to the 4th power. All right, so 1.8 divided by 27. This is 6.667 times 10 to the minus 20 equals S to the 4th power. So S is going to be the 4th root of 6.667 times 10 to the minus 20. I don't know about your calculators, how your calculators work, but I have to take this number to a power. Remember, the 4th root of that is the same as this number to the 1/4 power. Right? Remember that from math class? You don't remember that? All right. Take my word for it then. Okay. So when I stick it in my calculator, I'm going to take this one, 6.7 times 10 to the minus 20 to the 1/4 power. Now your calculators may have a root function. Right? It'll have like a square right here. It'll do like that on your button. And you punch in that value for and get your value. But I have to take this to the 1/4 power. So I'm going to say that enter. So 1/4 is 0.25. And then I click my y to the x power. And I get S equals 1.6 times 10 to the minus 5 molar. That's the molar solubility of silver phosphate. Right, compared to 1.3 times 10 to the minus 5. So this is more soluble than silver chloride by a little bit. See, there it is. Okay, everybody find that key on your calculator?
Keep telling me error on mine.
Let me see.
So I'll put 4, and then I'll push the little that, and I'll be 4, and then second do that one, and I'll put in the numbers that says there. So maybe it's not
number first.
So I'm not sure if I'm just completely going wrong.
6, 6, 6, 7, and then your exponent is what? Just times.
Yeah.
6.667 times 10 to the minus.
So I'll do this how I did it. So I did 4 like that, and I did 6.6 or 6.667 times 10 negative 20. Loaded it. And then it says there
Oh, okay. So punch in the 6.667 times 10 to the 20. Now, okay. Now get the root cube.
This one or this one?
The one that, this one, or this one. Then put in the value. 4.
One. Overflow air.
All right, it's time to look at the user's manual.
Okay, yeah.
Anybody else have trouble with that? No? Okay. So that's how we go from the KSP value, solubility product, to the actual solubility. Okay. How does the solubility of silver chloride in water compare to that of silver chloride in acidic solution? Right. I said we were going to stay in aqueous solution, but that doesn't mean we can't acidify the solution. Right. We can't add hydrogen ions to it and see what effect it has on it. Here we're getting to the when we change the nature of the solution, it's not just pure water anymore, but there's something else in there already, or we add something to it. Then we're looking at either common ion effect or coupled reactions. I knew it'd come to me eventually. Or coupled reactions. So in this case, if we've got silver chloride in water, right, our expression is going to look like this. Aqueous solution, chloride. And then we're going to add nitric acid. So we've got H plus and nitrate, right? Nitric acid is completely soluble. It's a strong acid. So you're only going to have hydrogen ions and nitrate. So can nitrate interact with any of those? No. It's not going to interact with this, and silver nitrate is completely soluble. So nitrate's not going to influence this at all. How about hydrogen ions? Will hydrogen ions interact with this anion? No. Hydrochloric acid is a strong acid. It's completely soluble. So addition of this acid in this form has no impact on the solubility. Right? It doesn't couple in any way that will shift the equilibrium to one side or the other. Now, what if instead of nitric acid, we used hydrochloric acid? Now you've got a common ion, right? The hydrogen isn't the culprit, the chloride ions. If you add chloride ion here, you're adding more here. That shifts the equilibrium which way? That way. So it will reduce the solubility. If you add hydrochloric acid instead of nitric acid, you will shift the equilibrium to reduce its solubility. All right. So does that have any impact on the solubility product? No, it's a constant. Right? Solubility will change, but the constant doesn't change. All right, I think that's where we're headed after this discussion. Here we've taken the opportunity, and there's that square box again. That's supposed to be a double barbed arrow. When we add them all together, you get no change, right? There are no common ions involved. If on the other hand, we do, okay, we talked about this one where we changed the acid to chloride. What if we're talking about, let's do this, silver phosphate? Oops. There. And phosphate on this side. Okay. What if we add nitric acid to this one? remember, what is phosphate? It's the conjugate base of a weak acid, right? So phosphate would be the conjugate base of this weak acid. Right, in equilibrium, and these are aqueous solution. So this has hydrogen ions and phosphate. Okay. So what does that say about that in terms of acidity or basicity? If this is a weak acid, that's a strong base, which means it wants hydrogen ions wherever it can find them. So if we put hydrogen ions in there, we're going to get this attached with that going in this direction. We're consuming phosphate ions and we shift the equilibrium that way because we're removing phosphate. We're converting it to this, which isn't part of that equilibrium. Right? So if we remove this by adding acid, we're going to shift the equilibrium that way and increase the solubility. So that's characteristic. Anytime you have a solid that produces a strong base as the anion, then all you have to do is add hydrogen ions and you'll increase its solubility. That's one way to increase solubility. If the anion in solution is a strong base. All right, so there we have the explanation. So this is just a reminder, KSP doesn't change. KSP is the same. As long as the temperature is constant, KSP will not change. All right. Calculate the solubility of silver chloride in 100 milliliters of 4 times 10 to the minus third molar calcium chloride. Excuse me. All right. The expression that's related to the KSP is still this one that I just erased. Okay. So if we set up our ice table like that, we start off with how much of these? What's the initial concentration of these? Well, when we first put this into solution, there's no silver in that solution. But is there chloride? Yeah, there's chloride. You have 4 times 10 to the minus third calcium chloride. And this is completely soluble. Okay. So what's the concentration of chloride? When you put that in solution, you get 2 chlorides for every 1 molecule. So the concentration is actually 8 times 10 to the minus third. Everybody see that? We've doubled the concentration of chloride. When this goes into solution, you get 2 for 1. 2 chlorides for every 1 molecule. So that means the concentration of chloride is 8 times 10 to the minus third. Okay, those are our starting conditions. Right now we're going to, since this is 0, the shift is going to be that direction. We don't have to calculate the Q. We know since this is 0, it's going to move that way. So we're going to get, for every one of these, we're going to get one of those. And we're going to get one of these. All right, so at equilibrium, we have S here, and we have 8 times 10 to the minus third plus S. Okay. Now we can set up our equilibrium expression, 1.6 times 10 to the minus 10. Let's see, I'm gonna need some more room. 1.6 times 10 to the minus 10 equals silver concentration, S, times chloride concentration, 8 times 10 to the minus third plus S. Okay. Now, if you don't want to use a quadratic, right, because S times S is S squared and S times that is an S, so you're going to have your quadratic set up there. You can do that. But can we say that the solubility is going to be, what is it going to be relative to this one, 10 to the minus third? Well, let's look back. What was it when it was pure water? All right, we can surmise that if we've already got chloride in here, that the equilibrium is not going to shift as far to the right. You've already got a common ion there. Right? So it's going to keep the concentration, the solubility low. Right? But if it started off at, let's see, let's go back. It started off at 10 to the minus 5. 10 to the minus 5 is still 2 orders of magnitude less. So it's going to be a lot less than that. I think we can ignore that value. Yeah. Okay, there's our setup. Right. So that's what I did in the slide. We ignored this value and said it's approximately 8 times 10 to the minus third S, because we said that's too small to worry about. So that means S is going to be equal to this times 10 to the minus 10 divided by 8 times 10 to the minus 3. All right. So, well, I don't need to calculate, it's right there. 2 times 10 to the minus 8 is the molar solubility of silver chloride if there's already this much chloride ion in solution. So it did drop it quite a bit, right? 3 orders of magnitude decrease in concentration. Oh, by the way, 100 milliliters doesn't matter. This is an intensive calculation. So it could have been, since we already know the molar concentration of calcium chloride, the volume doesn't matter. Now, if we knew an absolute amount of calcium chloride in a given volume, then you'd have to calculate the concentration in order to proceed. Then the volume would matter. But in this case, the volume is extra. We don't need it. All right. How about if we have 4 times 10 to the minus third molar calcium nitrate? Well, if we've got 4 times 10 to the minus third calcium nitrate, is there a common ion there? No. Calcium chloride is completely soluble. So the calcium ions aren't going to have an effect. Nitrate and silver nitrate is completely soluble. So this concentration has no effect on the solubility. There's no common ion there to affect the equilibrium. All right. So we're back at 1.3 times 10 to the minus 5 molar solubility. All right. So we didn't need to use Q, but that doesn't mean we gave up on Q, because Q is a valuable bit of information. If we're trying to decide whether or not, now we're looking at mixtures of ions. If we have 2 solutions say we have a silver nitrate solution over here and a sodium chloride solution over here. We mix them together. We want to know, is the concentration high enough so that we will get precipitation? Because if the concentration is too low, then it will not precipitate. It won't move to the solid side. Right? And we do that by comparing the Q and the KSP. So if we say, let's see, don't we have an example? Yeah, there's our example. So you remember how to calculate Q. I'll stop erasing this thing because I have to move on. Okay. So the Q is equal to the actual concentration of silver ions times chloride ions. Right? So compared to KSP, what we want to do is say, if the Q, this concentration is larger than the KSP, right? That means we've got too much on this side and it's going to move back that way and we'll get some precipitation. But if Q is smaller than the KSP, that means there's not enough on this side and we won't get precipitation. Okay. If that logic evades you, just memorize it. If Q is greater than KSP, you get precipitation. If Q is less than KSP, you don't. All right. So this relationship between the Q value and the KSP of each of the salts of different metals in solution can be used to separate those metals from a mixture. Here we're taking a very simple selective precipitation of only two metals, barium and silver. If we add hydrochloric acid, that will form a precipitate with silver, as long as we have enough of it, right? We add enough chloride to exceed the Q, the KSP. If we add enough of this, so that now the concentration of that in solution and that in solution exceeds KSP, then we'll precipitate silver as the silver chloride salt. And you'll see it drop out of solution. And when it does, barium stays in solution because barium chloride is soluble. Okay, so how do we get them apart? Okay. I mean, it's great. We got silver chloride precipitated on the bottom. How do you separate them now? Well, how about filtration? Right. Filtration separates based on particle size, and barium is not even a particle. So you just filter it through a paper or a medium that has small enough pore size to catch all your crystals of silver chloride, and then you've got a solution of barium here and a solid silver chloride over here. You separated the two. All right. Now, all we need is chloride ions in that solution to precipitate out the silver. Why don't we use salt? Right? That's safer to use than hydrochloric acid. Why don't we use salt? Table salt. Well, you could do that if all you want is the silver. Right? You get the silver out of it. You don't care about the barium. But if you want to recover the barium too, you don't want to contaminate your barium with sodium. So that's why we use hydrochloric acid to actually separate the two metals and recover both of them. All right. Now we got a more complicated mixture. We've got copper 2+, mercury 2+, nickel 2+, and manganese 2+. If we use hydrogen sulfide, we know that sulfides of some of the metals are insoluble. Or they're only soluble at large concentrations of sulfide. Right? They have different KSPs for the sulfides. You would have a different KSP for that sulfide. Let's see, we've got mercury, nickel, and manganese. Mercury, nickel, and manganese. And these would all be solids. So how do we separate them if we're only going to use hydrogen sulfide? Well, you want to control the concentration of sulfide so that you also control the Q value. Right? You want to precipitate the ones that have the lowest solubility sulfides. So you adjust your solution so that the sulfide concentration is very low, but it's still high enough to precipitate the metals whose sulfides are very, very insoluble. You only need a little bit of sulfide. So how do we do that? Here we go. You adjust the pH. Right? If you've got hydrogen sulfide in solution, and it's in equilibrium with that and that, right? These are aqueous. Yes, they're all aqueous. If you want to reduce the concentration of sulfide so that it's very low, and it'll only precipitate the metals that are extremely insoluble as sulfides, which would, in this case, would be the copper and this one. These have the least solubility of sulfides. Then we just add acid. Right? We have to add acid in some form that doesn't, let's see, all these, manganese, nickel. We typically don't add chloride yet. So this would be maybe nitric acid, because all nitrates are soluble. So we don't have to worry about that one. If we add this one, that increases this, drives the reaction that way, and reduces the concentration of sulfide. So we acidify the solution with hydrogen sulfide. And that will precipitate only these two and leave these two in solution. Okay? Because their K values are, well, this is the K value for hydrogen sulfide. Overall K is 1.2 times 10 to the minus 20. That would be for this equation. So we're consuming sulfide by adding hydrogen ions. Then if we want to increase the concentration of sulfide, so now once we've separated these out, right, we filtered them out, now we want to get these two. All you have to do is shift the equilibrium back that direction. So how do we do that? Just add a base. Right. That will consume hydrogen ions, drive the reaction back this way, and increase your sulfide. Then you can precipitate the other two out. All right, so that's what the decision tree would look like. Right? If you add hydrogen sulfide to this mixture at a pH of about 2, then you will precipitate out only the copper and the mercury. Then you add hydroxyl to a pH of 8, and you can precipitate out the manganese and the nickel. Selective precipitation. This is what a scheme looks like for a large mixture of metals. Say you've taken you're a bench chemist for a mining company. You've taken their ore sample and you've dissolved it, completely dissolved it. I mean, it might take something pretty aggressive, like hydrofluoric acid, maybe some hydrochloric acid, nitric acid, you know, and you get it in solution. Then you want to separate the metals. Well, the first step is to get these grouped out, separated out. So in this case, we want to separate out the chloride salts. So that's silver, mercury 1, and lead 2+ in this group, and they're color coded. So at the top, you've got the purples, and the first step is to add hydrogen chloride, hydrochloric acid. That will separate out those 3 as chloride salts. Okay, when they precipitate, just filter them out. Then you go to the next step. Now your solution is already acidified. So when you add hydrogen sulfide to it, you bubble it through probably, or maybe you have a concentrated solution that you add. But under acidic conditions, now you're only going to precipitate out the very, very strongly or very weak solubility sulfides. And that's a whole group of them there in the second row. Then you add base, right? If you add base, then the other sulfides come out. And what do you have left over? Well, you have barium, calcium, and magnesium don't precipitate as sulfides. Barium sulfide, calcium sulfide, and magnesium sulfide are all soluble. So we add sodium carbonate. Sodium carbonate is fine because your solution's already basic. And sodium carbonate is a base. Right? If you remember? If you combine sodium and carbonate, right, from a strong base and a weak acid, you get a basic solution, right? So it's already basic. You just add some of this to it. You don't change the pH that much, but you do add the carbonate. And the carbonate will precipitate barium, calcium, and magnesium. Now, what do you got left in solution? You got the alkali metals, sodium, potassium, and ammonium. Those are still in solution. Now, these are grouped. You have 5 groups of extracts, so to speak. So what do you do then? Well, if you want to separate them even further, then you have to go through other procedures, right? That's beyond this course. You go to other procedures and you take each one of those groups and then you use different procedures to separate those. That's the way wet chemists used to work. Right. Nowadays, we have analytical equipment that'll tell you how much of each metal is in the solution. It's just like that. I used to use one called an inductively coupled argon plasma spectrometer. You just get those metals in solution, suck them into your machine, and it spits out the answers after you calibrate it, of course. Before that, we had to use atomic absorption spectrophotometers. So we'd aspirate the solution through an acetylene, air acetylene flame, and we'd shine a light through it that is particular to each of the elements, and we'd have to do each element in sequence. It took a lot longer. The plasma spectrometer is a whole lot faster and more expensive. I think the last one we bought was like $185,000, which is pretty cheap because the one that I used when I first arrived there was $250,000. But the price came down and the quality went up. Okay. And the reason we spent so much money on it is because most of the scientists I was serving in that lab were interested in elemental composition. If we had 15 research scientists. If most of them hadn't been interested in it, then they couldn't justify spending that much money. But since they did, we went ahead with it. All right. Now that's solubility. Remember, if you're solid produces a strong base as an anion, all you have to do to increase the solubility is add protons, right? Add acid. But we witnessed a case where adding an acid wouldn't help us, right? Silver chloride, add acid, doesn't do anything, doesn't change the solubility. Silver phosphate, yeah, because the phosphate ion is a strong base. But how do you get silver chloride in solution? That's what we're going to do Thursday. You form a complex ion with the metal. You don't attack the anion. You attack the cation. So we're going to solubilize more of the silver chloride by removing I think I've learned by now, just leave it up here. We're going to shift the equilibrium that way, not by attacking that, but attacking this. And we're going to form a complex ion with it. Silver, see, diamine silver 1. Diamino silver 1. Let's see. 2 of these and plus charge. And this is in aqueous solution, but it's removed from that equilibrium. It's got an equilibrium of its own. So if we have, it takes a lot of this to do that, like, I don't know, between 2 and 10 molar. It's pretty high, but still, you shift the equilibrium this way and you can completely solubilize all the silver chloride solid with ammonia. Now let's see. I gave you a couple of handouts here. You don't have to memorize these things. This is just information. These are the solubility products for a lot of different solids. These are naming conventions. You ever have to name a complex ion, then go to that. Okay, so those are the 2 ways you solubilize a slightly soluble compound, right? You either add acid if the anion is a strong base, or you complex the cation. And this equilibrium right here has its own formation constant. So the concentration of diamino silver ion, right, divided by silver ion concentration and ammonia concentration squared. That would be the formation constant, and this is what we're after, I think. Yeah, formation. We're after this on Thursday. We'll find out what that is. We should have time after the review on Thursday to talk about this, to kind of orient you toward it. Here's an example of and remember, this is the overall equation. That plus that yields this. But this is like acids. When acids dissociate, they do 1 proton at a time. So if you have phosphoric acid, you get a proton and dihydrogen phosphate ion. And then the dihydrogen phosphate gives you another proton plus a monohydrogen phosphate. And then the monohydrogen phosphate gives you another hydrogen ion plus the phosphate anion. Same concept works for this formation of a complex ion. In this case, beryllium is being complexed with the fluoride ion. So we get an equilibrium constant for the first association of fluoride with beryllium. And then we take that product and complex with another fluoride. It has its K, and same for the third one and the fourth one. Notice that all of those K values are large positive values. Right? So the shift is always to the right. So once we form that first one, it goes into the next one and it's immediately shifted to the right by a huge margin. And the same thing for the third and fourth one. That's one way to look at it. The other way is to combine them all. And what's the overall K? Right? So how do you find the overall K? you multiply the K's, right? You multiply each one of those K's to give you this overall equation, and you get 10 to the 12th is the formation constant for that complex ion. Tetrafluoroberyllium. Let's see, beryllium is 2+. All right. So these are the two strategies for solubilizing a salt. If you have a very good or strong base as a consequence, like phosphate, then you just acidify it, no problem. If you don't, then you have to go to a complex ion. Those are the two strategies for solubilizing sparingly soluble salts. Let's see. Do we have time to listen to Saul? How much time? We only have a half hour now. Yeah. Let me see. How many more slides do I have after this? Just 4. Okay. I think we got time to listen to him. See, let me turn the volume up.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ICE table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So if we're losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1:1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the negative 10. So we put in here 1.8 times 10 to the negative 10. And this is equal to, this would be x times x. So this is equal to x squared. So we can get out the calculator and solve for x. So we have the square root of 1.8 times 10 to the negative 10. So we take the square root of that, and x is equal to 1.3 times 10 to the negative 5 if we round that. So x is equal to 1.3 times 10 to the negative 5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So not very, it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? Right, we get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver plus 1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver plus 1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver plus 1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening. All right? So we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right, we have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those 2 reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add 2 reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those 2 reactions. So K is equal to Ksp times Kf. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia. So let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ion. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here, so we leave silver chloride out because that's a solid, right? But we have ammonia, so this is all over the concentration of our reactant, so this is over the concentration of ammonia. And notice our coefficient is a 2, so we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is X, and our equilibrium concentration of chloride anion is X. So on the right side, we would have X to the first power times X to the, let me take that out, times X to the first power. Right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 0.6 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x, right? So we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar. Right, so that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride. Right, so it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
The example that we got in the slides, that's why I put all this up here first, because it was actually running parallel to what Saul Kahn was talking about. But if we combine those three equations into one, we get the solubility equation for silver chloride in ammonia. Right, and there, I calculated the KSPs for each one of these as 2.8 times 10 to the minus third. Saul came up with 2.9. Pretty close. So if we combine all those and we get this equation with, well, 2.75, actually, I rounded it because of significant figures. So the KEQ is that value, and there's the expression for it. If we set it up here, and instead of doing 3 molar ammonia, oh, one comment before we switch slides. The K value for this overall reaction is 10 to the minus third. It's better than the KSP for silver chloride by about, what, 7 orders of magnitude. But it's still kind of low. That's why we have to have a large amount of ammonia to give us enough of this and this in the denominator to give us that value. So the solubility of silver chloride increases considerably if you use a lot of ammonia. So here's an example where we have 10 molar. Right? Instead of 3 molar, if we use 10 molar, we're starting off with 10 molar, and we don't have any initial here and here. Then we're going to solubilize it by losing, well, for every one of these that we produce, right? The ratio here is one of those for one of these, 1 silver, 1 silver. So if we set up our unknown as our solubility here, and then this is also going to be an addition to solubility, then we lose 2 of the ammonia for every one of those. So at equilibrium, we have 10 minus 2 S, and we have S and S. So that's where those values come from in this expression. Right? We have S squared over 10 minus 2x squared. And the nice thing about it is, since the numerator and the denominator are both squared, we can pull that square outside. We don't have to deal with a quadratic in this case, or even an estimation. An estimation would be difficult because that x would be pretty large. All right, so once all the math is done, we find out the solubility now at 10 molar ammonia is, wait for it, 0.47. So the solubility at 10 molar S 0.47 molar at 10 molar ammonia. And what was it for 3 molar? 0.14, I think. Wasn't it? Oh, it's not on the slide. I think it was. I think it was 0.14 molar at 3 molar ammonia. So we quadrupled our solubility by tripling, a little more than tripling the ammonia concentration. Now, I just threw this in for fun. How much ammonia is left in solution? Right. Well, 10 minus 2s is how much was used up. We started at 10, so 10 minus 2s subtracted from 10 gives us 9 molar left. So you still got 9 molar ammonia in solution. That's why when you form this complex ion, you take a whiff of it, right? And it'll knock you back because you still got lots of ammonia there. That's it.